Speed feels simple. It feels almost too simple to question. If something moves, you measure how far it travels and how long it takes. Divide distance by time and you have your answer. If you start moving while observing it, the number changes. Speeds add, speeds subtract. Everything about motion seems flexible, dependent on perspective. If you are standing still and a train passes you at 60 miles per hour, that is its speed. But if you are inside another train moving in the opposite direction, the speed feels faster. If you chase it from behind, it feels slower. This is not controversial. It is not philosophical. It is obvious. Motion is relative. The universe does not privilege one observer over another. For centuries, this understanding worked beautifully. Galileo formalized it. Newton built mechanics on top of it. The idea that velocities combine depending on who is measuring them became part of the invisible scaffolding of science. You could launch cannons from moving ships. You could predict planetary orbits. The rules held steady. And then light entered the story. Light behaves like something that moves. It travels from the sun to Earth. It crosses rooms, reflects off mirrors, enters telescopes. It takes time to arrive. So naturally, we treat it like every other moving thing. If a flashlight emits a beam, and you move toward that beam, you expect it to approach you faster. If you move away, you expect it to chase you more slowly. This expectation is not careless thinking. It is the logical extension of everything we know about motion. If speeds always combine, then your motion must affect the measured speed of light. There is no special exemption clause in classical physics. But when scientists began measuring it carefully, something deeply unsettling happened. No matter how fast the source moved, no matter how fast the observer moved, no matter the direction, the speed of light remained the same. Not approximately the same, not close enough, exactly the same. 300 million meters per second, over and over again. To first glance, this sounds like a technical detail, a curious result, but it is not. It is a fracture in the logic of motion itself, because if speeds combine for everything else, and light's speed does not combine, then one of two things must be true. Either light is not behaving like an ordinary moving object, or our understanding of motion is incomplete. And this is where the discomfort begins. We trust everyday intuition because it works. Throw a ball forward on a moving train, and it travels faster relative to the ground. Fire a bullet from a plane, and its speed adds to the plane's velocity. These examples are not rare exceptions. They are the rule. The universe seems built on this principle. But light refuses to participate. You can chase it at unimaginable speeds. You can run toward it. You can observe it from a moving platform. It does not care. It does not adjust. It does not negotiate. It remains constant, as if the universe has drawn a line and declared this number untouchable. The strange part is not that light is fast. The strange part is that its speed is immune to perspective. And if perspective does not change it, then something far deeper must be absorbing the difference. This is the moment where comfortable physics begins to crack, because if you cannot alter the speed of light by changing your motion, then motion itself cannot be what we thought it was. The assumption that speeds simply add together begins to look less like a universal truth and more like an approximation, one that works only under limited conditions. For everyday objects, the illusion holds. For light, it collapses. And when an illusion collapses, it forces a choice. You can dismiss the anomaly, or you can follow it wherever it leads. Physicists chose to follow it. What they discovered was not just a correction to a formula. It was a restructuring of reality's foundations. But before that restructuring could occur, they had to confront a deeper puzzle, one that experiments would make impossible to ignore. Once the paradox was clear, the next step seemed straightforward. If intuition insists that speeds combine, then the effect should be measurable. Perhaps the differences were simply too small to notice at first. With careful instruments and controlled conditions, the variation in light speed should reveal itself. Physicists were confident. They were not chasing mystery. They were chasing precision. At the time, there was a widely accepted assumption about how light traveled. It was believed to move through something, an invisible medium filling all of space, often called the ether. Just as sound moves through air and waves move through water, light was expected to ripple through this subtle background substance. If that were true, then Earth itself must be moving through this ether as it orbited the sun. And if Earth was moving through it, then a beam of light traveling in the direction of Earth's motion should behave differently from a beam traveling perpendicular to it. The logic was clean. If you run into the wind, you feel resistance. If you run with it, you feel less. The same principle should apply to light moving through the ether. There should be a detectable shift in its speed, depending on direction. So an experiment was designed. Elegant, precise, almost inevitable. A beam of light would be split into two perpendicular paths. Each beam would travel outward, reflect off mirrors, and recombine. If one beam experienced even a tiny delay compared to the other, due to Earth's motion through the ether, the interference pattern would shift. The difference would be measurable. Everything about the setup suggested success. The reasoning was sound. The mathematics predicted a clear outcome. And then nothing happened. No shift. No variation. No evidence of motion through any medium at all. The result was not dramatic. There was no explosion, no instrument failure. The apparatus worked exactly as intended. It simply refused to confirm the expectation. The interference pattern remained stubbornly unchanged. At first this was unsettling, but not catastrophic. Perhaps the effect was smaller than predicted. Perhaps the ether moved along with Earth. Perhaps the experiment needed refinement. So it was repeated, improved, made more sensitive. The outcome remained the same. What made this so disturbing was not that a theory had failed. The history of science is filled with failed theories. What made it disturbing was that the failure was silent and consistent. Reality did not offer partial agreement or ambiguous hints. It offered clean refusal. The expected difference in light speed was not merely difficult to detect, it was absent. And if there was no ether wind, then light was not moving through a background medium at all. But if light was not moving through something, then what did its motion even mean? Motion is always defined relative to something. Remove the background, and the concept begins to wobble. The deeper implication began to emerge slowly. If no experiment could detect Earth's motion relative to light, then perhaps light did not require a reference frame in the traditional sense. Perhaps its speed was not relative to a medium. Perhaps it was absolute in a way nothing else was. This possibility was more radical than it sounded, because if light speed was the same for every observer, regardless of motion, then the principle that velocities combine could not be universally true. The experiment that should have worked had done something far more disruptive. It had exposed a hidden assumption. Scientists had assumed that space itself provided a fixed backdrop, a silent stage against which motion could be measured. But if light ignored that stage entirely, then the stage itself might not exist in the way they imagine. The problem was no longer about detecting ether. It was about understanding why the universe refused to provide one dot. At this point, physics stood at an uncomfortable crossroads. Either cling to increasingly complicated explanations to preserve classical intuition, or accept that the intuition itself might be flawed. The experiment did not scream its conclusion. It whispered it, but the whisper was persistent. If light speed does not change when the observer moves, then perhaps the observer's measurements of space and time are what change instead. That possibility sounded almost absurd. Space does not stretch just because you move. Time does not slow down because you accelerate. These ideas felt closer to philosophy than physics, and yet they were the only way to preserve the one thing the experiment had made undeniable. Light refuses to slow down. If light refuses to change its speed, then something else must. That was the quiet realization sitting beneath the failed experiments. The instruments were working. The mathematics was consistent. The contradiction was not in the data. It was in the assumptions about space and time. For centuries, space had been treated as a rigid arena, a vast unmoving stage where events unfolded. Time flowed uniformly for everyone, everywhere, like a universal clock ticking in the background of existence. You could disagree about motion, but you could not disagree about distance or duration. Those were fixed. But if two observers moving relative to one another both measure light traveling at exactly the same speed, something impossible seems to happen. Imagine one observer standing still and another racing forward at high velocity. A flash of light moves away from both of them. Classical intuition insists the moving observer should measure the light as traveling slower relative to them. Yet they do not. If speed equals distance divided by time and the speed stays constant for both observers, then either their measured distances differ or their measured times differ, or both. This is where intuition fractures. The only way to preserve the constancy of light speed is to allow distance and time themselves to adjust depending on motion. The faster you move, the more space contracts in the direction of that motion. The faster you move, the slower your clock ticks relative to someone at rest. These are not observational illusions. They are structural consequences. The universe compensates. What makes this revelation so unsettling is how indirect it feels. Nothing about everyday experience prepares us for flexible space or elastic time. At ordinary speeds, the effects are too small to notice. A car traveling down a highway does not visibly shrink. A person running does not experience time in slow motion. Reality appears solid. But at speeds approaching that of light, the effects become undeniable. Clocks carried on fast-moving spacecraft tick measurably slower than clocks on Earth. Particles accelerated in laboratories live longer than they would at rest, because time for them genuinely slows down. This is not poetic language. It is experimentally verified. Feynman emphasized something crucial about this shift. The universe is not performing magic. It is not bending rules arbitrarily. It is obeying a deeper consistency. If the speed of light is the same for everyone, then space and time must organize themselves in such a way that this statement remains true. It is not that light is special in a sentimental sense. It is that the structure of space-time demands invariance. The concept of simultaneity collapses under this realization. Two events that appear to occur at the same time for one observer may not occur simultaneously for another moving observer. There is no universal now stretching across the cosmos. Each observer carries their own slicing of time, determined by motion. This is where the betrayal feels personal. We rely on the idea of shared time. We assume that the present moment is universal. But relativity dissolves that comfort. The present becomes relative. Agreement about time becomes conditional. And yet nothing becomes chaotic. The mathematics is precise. The geometry is consistent. Space and time fuse into a four-dimensional structure, space-time, where intervals remain invariant, even though distances and durations shift. Instead of protecting our intuition, reality protects consistency. The faster you move through space, the slower you move through time. Not because of mechanical resistance, not because of hidden friction, but because motion itself is a rotation within space-time's geometry. Change one component, and the other must respond. Light, having no mass, occupies an extreme position in this geometry. It travels entirely along the boundary of space-time structure. Its motion through space is maximal, leaving no motion available through time. In that sense, light does not experience time passing between emission and absorption. This idea feels almost mystical, but it is not. It is the logical endpoint of taking the constancy of light seriously. Space contracts, time dilates, simultaneity dissolves, and all of it happens quietly, automatically, to protect a single invariant speed. At this stage, the question shifts again. If space-time is willing to bend itself to preserve this constant, then that constant must represent more than just the speed of a beam. It must define the architecture of causality itself. Light is not merely moving through reality. It is outlining its limits. By now, the story has inverted itself. We began by asking why light refuses to slow down, as if light were being stubborn. But once space contracts and time dilates to preserve its speed, the question changes. It is no longer about resistance. It is about structure. Quest. The deeper truth is this: light is not moving through space in the way ordinary objects do. When a car drives down a road, it moves through space, while time passes normally for it. When a person walks across a room, distance changes, and seconds tick forward in a familiar rhythm. Massive objects always divide their motion between space and time. The faster they move through space, the slower they move through time. But both components are always present. Light is different. According to relativity, light does not experience time. From the photon's perspective, if such a perspective could even be meaningfully described, the moment it is emitted and the moment it is absorbed are not separated by duration. The journey across millions of miles, or even billions of light years, contains no passage of time for light itself. This is not philosophical exaggeration. It follows directly from the geometry of space-time. As an object approaches the speed of light, time for that object slows relative to stationary observers. Push that motion to the limit, to light speed, and time dilation becomes total. For light, the interval of time between departure and arrival collapses to zero. This is where intuition struggles again. We imagine light leaving a distant star, traveling for millions of years, and finally reaching Earth. From our perspective, that is exactly what happens. But from light's own structural position in space-time, emission and absorption are directly connected, not sequential in time, but linked across geometry. In that sense, light is less like a traveler and more like a connector dot. This reframes the entire question. Asking why light does not slow down assumes it is capable of slowing, that it has room within space-time to trade some motion through space for motion through time. But it does not. Light already occupies the boundary condition. It moves entirely along space-time's limiting structure. There is no slower state available to it without ceasing to be what it is. Massive objects can slow down because they have internal time. They possess rest mass, which anchors them to a frame where time flows normally. Light has no rest mass. There is no frame in which a photon is at rest. To be at rest would require time to pass normally for it. And that configuration simply does not exist. This is why slowing light is not just difficult. It is conceptually incoherent within relativity. To reduce its speed would require introducing a rest frame for something that cannot have one dot. The unsettling realization is that light is not obeying a rule imposed from outside. It is expressing the limit condition of space-time itself. When we say the speed of light is constant, we often imagine it as a physical property like density or charge. But it is deeper than that. It is the conversion factor between space and time. It defines how much distance corresponds to how much duration. It stitches the two together into a single structure, dot. Light does not move through space the way matter does. It traces the edges of what motion is allowed to mean, dot. And once this becomes clear, the refusal of light to slow down no longer feels like defiance. It feels inevitable, dot, because light is not racing through a pre-existing arena, dot. It is revealing the shape of the arena itself, dot. At this point, the question is no longer why light refuses to slow down. The real question is what would happen if it did, dot. Imagine, comma. For a moment, that light could move just a little slower, depending on who observed it. Imagine its speed behaved like every other velocity. Adjustable, relative, negotiable. At first, nothing dramatic seems to follow. A beam would simply arrive slightly sooner or later depending on motion. But beneath that small change, something catastrophic would unfold. Because the speed of light is not merely about illumination. It is about causality. Every cause produces an effect. Every signal travels. Every force propagates. The speed of light sets the maximum rate at which influence itself can move through the universe. It defines how quickly information can travel from one event to another. If that limit were flexible, then the ordering of events could become inconsistent. One observer might see event A cause event B. Another might see event B occur before event A. The sequence of cause and effect would fracture. Reality would no longer agree with itself. This is why the speed of light is not just a speed limit in the conventional sense. It is the structural boundary that preserves coherence. It protects the logical consistency of the universe. It ensures that causes precede effects in every frame of reference. When Feynman described physical laws, he emphasized something subtle. Nature is not obligated to satisfy human intuition. It is obligated only to remain internally consistent. The constancy of light's speed is not about elegance or beauty, though it possesses both. It is about necessity. Light defines the geometry of space-time. That geometry in turn defines which events can influence one another. Around every event in the universe exists a boundary, a light cone separating what can be affected from what cannot. Outside that boundary lies permanent separation. Inside it lies possible interaction. This structure is not optional. It is what allows the universe to function as a connected whole, rather than dissolving into contradiction. The refusal of light to slow down is therefore not stubbornness. It is stability. The light, slowed for some observers and sped up for others. Space-time could no longer preserve consistent intervals. Time dilation and length contraction would lose their precise balance. The elegant compensation that protects invariance would collapse. The deeper architecture would distort. And with it, the universe's internal agreement would unravel. Instead, what we find is something colder and more precise. A universe built not on shifting rules, but on geometric inevitability. The speed of light is woven into that geometry. It is the conversion factor between space and time. It is the constant that ensures no observer can rewrite causality by changing velocity. This realization carries a quiet weight. Light is not fast because it is energetic. It is not constant because it is privileged. It is constant because reality would lose coherence without that constancy. The deeper truth Feynman illuminated was not mystical. It was structural. When you follow the equations honestly, without forcing intuition to lead, you discover that light's speed emerges from the way space-time itself is organized. And that organization does not bend for perspective. In the end, light does not refuse to slow down out of resistance. It does so because slowing down would mean becoming something that space-time cannot accommodate. It would require a different geometry, a different universe, a different logic of cause and effect. So light remains at its limit, not racing, not straining, simply expressing the deepest constraint embedded in existence. The unsettling part is that the universe is built in such a way that it must be.